Okay, everyone, welcome to Gravity. This is chapter 13. We've got a lot of stuff to cover, so I wanted to get this one down. And then you can go back through and read it, watch it over and over and over, however many times you need to. Okay, so we're going to start off with Newton's universal law of gravitation. I've got it right down here at the bottom, and I'm not sliding up because I've got other stuff below that. The force of 1, 2, all right, so here's our mass 1 and our mass 2. So this could be a star, and this could be a planet, right? But it could be anything. Two different masses, doesn't matter. You take the masses, you multiply them together, and you're going to divide by the distance between them. That's this distance here. So we call it R12, distance between 1 and 2, and we square that. And then we multiply by the universal gravitational constant. And of course, that's going to be in the direction of r hat. So that's the r hat direction. That's for r hat for 1, and then this is r hat for 2. But, you know, we're not going to care too much about that as long as you're doing it radially, and one of them is larger than the other. And the center of mass, from the center of mass of the objects, r points out at all times. So it'll always be in that radial direction. Let's just put it that way. So let's talk about the universal gravitational constant. So we've got it right here. G equals 6.67 times 10 to the minus 11, and that's newtons times a meter squared per kilogram squared. So when we look at this, these are the kilogram squareds, and they have to divide out because we only want newtons in the end, right? Because it's equal to a force. So the kilograms have to divide out. The meters squared have to cancel. So we've got meters squared in the numerator, kilograms in the denominator squared, because that's just how it has to be for this constant to give us newtons in the end. All right? So that's how that works, and hopefully that should be good. Now, why do we call this a universal law of gravitation and a universal constant? Well, it works not only at the 2-meter scale, okay, but it works at the galaxy scale. It works across the universe, right? Andromeda and the Milky Way are going to collide someday, and they're drawn toward each other because of gravity. So we've got atoms. Those also have gravity. Gravity's pulling them together, but the electromagnetic force dominates in that region. So we're not going to... it's so much bigger, okay? The electromagnetic force is so much bigger than gravity, which we'll see in a little bit, that at the atomic scale, gravity still works. It's just definitely harder to see. That's all. So let's do an example. We've got 2 space rocks. Hold on a second. Set timer for 45 minutes. Don't think you're going to get off the hook in 45. I might keep going. Okay, so example, 2 space rocks. All right, so here's the thing. We've got the sun in the middle right here. Okay, here's the sun blazing hot sun, and it's firing rays all over the solar system. Okay, it's super bright. We've got Mars right here, and we've got Jupiter out here. Okay. In between Mars and Jupiter, there's what we call the asteroid belt, and it just has a whole bunch of asteroids that, if you were to sum up all of their mass, it would equal 3% of the moon's mass. So they're pretty small, but the moon's pretty massive, I guess. There's not a lot of them, but they definitely mess with each other. So like two of them will come close to each other, and then one of them will spin off and then might even shoot in towards the Earth, right? That kind of stuff. But they're so small that we're not really worried about them. So here are our two space rocks. We've got a radius for one. We've got a radius for one. We've got a radius for the other. And we've got the mass of one, and we've got the mass of the other. Now, this mass is definitely bigger. M2 is bigger than M1. Okay, so just keep that in mind. All right, most of the time M1 is bigger than M2, but we're going to do M2 bigger than M1. And the radius, so imagine we are omnipotent, which means we are all powerful, and we could just take two asteroids and place them. I'm placing one there, and I'm placing one there, and they're 50 meters apart. So we just do it. Okay, so it looks kind of like this, and we get out of there, leave them undisturbed. We kind of just set them there and walk away. F21 is the force of 2 on 1. F12 is the force of 1 onto 2, and causing 2 to get closer to 1 here. And 1, of course, wants to get closer to 2. What is the gravitational force between them? That's the question. First part. So we do our universal law of gravitation. We plug in the numbers, and we get that equals 3.54 times 10 to the minus 3 newtons. All right. Well, that's great. What is their initial acceleration? Well, okay, so this guy being more massive over here, number 2, it's not going to this guy is not going to want to move as quickly as the first one. It's less massive. So the force is the same between them. We've got M2 times A02, and by 0, I'm just saying that it's the initial acceleration. So A02, all right? FG divided by M2 is going to give us this as our acceleration. So look at this, times 10 to the minus 9, right? So it's 5 times 10 to the minus 9. That is a pretty small acceleration. If we do it for M1, we get down here, and we're going to do this. Gives us this acceleration, same exact equation. This acceleration isn't as small, still pretty small, but it's not totally, it's a roughly, what is it, 4 times larger. So what is their final acceleration? So this is where I thought I was pausing last time, and ended up wasting everything that I recorded up to that point because I had to go get my calculator. So we're going to plug in these numbers and get the final. So we've got our 1.8, and we're going to multiply that 7.35 times that, and 6.5. Okay, well, let's talk about why is it 6.5. This is their final acceleration. So, oh, I didn't draw it out. Oh, I did draw it out. Okay. So right here, the two objects are about to collide. They're about to collide. But one has the radius of 2.5 meters, and the other has the radius of 4.0 meters. And right at the just the instant that they touch, they have this final acceleration. And we want to know what that is. So it's right as they're about to touch. They haven't touched yet, but they're just about to. So we're going to say that the radius between them, R12, is equal to 6.5 meters. Okay, so that's where this 6.5 comes in. And I'm going to divide now by 6.5 squared. Okay, 6.5 squared, and I'm going to divide by that, all right? And then we've got 10 to the 10 on the top. So we're going to multiply by 10 to the 10. And the gravitational constant, which is 6.67, we're going to multiply by that. And we also have to multiply by negative 11, 10 to the minus 11. So here's 11 negative 10 to the, and we'll multiply that in there, and we get 2.76, well, let's say 77 for 3 digits, times 10 to the minus 6, and that's newtons. So, why is our, what did I do? Why is our gravity higher? It should be much, this should be smaller than this. So what in the heck? I must have plugged something in wrong. All right. 1.8, enter. 7.35 times 6.5 squared, divide. Um, 6.67 times. And then we've got 11, so I should multiply by 10 to the minus 1, which would be divide by 10, and I'm left with 208 times 10 to the minus 3. That's so much better. Okay. So 208.8, let's say 209. 209 times 10 to the minus 3. Oh, yeah. Now we're almost 100 times bigger. Okay, so good. That makes sense. Awesome. So, what is their velocity at impact? You know what? Instead of doing that, I want to do what we did earlier and come up with the acceleration. And let's just do the acceleration. So let's do D. What is M1's acceleration as they're about to hit. So this is the final of 1. Okay? So let's do the same thing. We're going to say that A final of 1 is equal to our force of gravity divided by m1, and 209 times 10 to the minus 3 newtons, and we're going to divide that out by m1. Where is that number? Oh, 1.8 times 10 to the 5. Found it. 1.8 times 10 to the 5 kilograms. All right. Two oh nine, enter, 1.8, divide, and then we're going to have 10 to the 5 on the top. 10 to the minus 5 plus 10 to the minus 3 is 10 to the minus 8. So 8 minus 10 to the times, that'll be 1.6 times 10. 1.16 times 10 to the minus 6 meters per second squared. All right. And that's what we want. Okay. Let's do E. What is the velocity at impact? And we'll just use the velocity of m1 at impact. All right. So we can do one of my most favorite things, and we can start off with V final is what we really want. V initial we're going to say is 0. And we're going to add 2 times the acceleration. So we're just going to use AF. No, we can't use AF1. We have to use A average. And that's going to be equal to 1/2 A initial of 1 plus A final of 1. So we want A average. A average. And then that's our delta X, which is 50. What's our average? What is that equal? Boom, boom, boom. I might be wrong about this, but I have notes that say 5.92 times 10 to the minus 7. 5.92 times 10 to the minus 7. And of course, that's meters per second squared. So I think we should go with that. I don't want to do any more calculating. If that's not correct, I'm sure you guys can find out and put the right one in. But either way, we're going to be close. So we've got a 0 there. So really, that equation turns into V final is equal to 2 times A average times delta X. And we're going to be taking the square root of it. So V final is 2 times 5.92 times 10 to the minus 7 and we're multiplying by our delta x. Okay, so I didn't figure out what our delta x is. So here's one mass, here's the other. These guys are 50 meters apart from center of mass to center of mass. How far, though, did they go, right, toward each other? They went everything except for that last 6.5 meters. So 50 minus 6.5, 50 minus 7 is 43. So that's 43.5 meters is our delta x. Okay, I hope that makes sense. And so we're going to say 43.5, and we're going to take a square root there, and we'll have this 7.17 times 10 to the minus 3 meters per second. So really, really slow, okay, when they finally do touch each other. It's so slow that they're probably going to touch each other and then just stick basically like this. There's not a lot of momentum. There's not a lot of deformation going to happen. So the two objects will just kind of stick together like that. And that's pretty much the end of it. That's the way they'll be for a long time. All right, so F. You guys didn't think I could come up with one, but I did it. How long will it take for them to collide? How much time does this whole thing take? Okay, so x equals vt, right? We can also use, okay, so we can use a couple of things. We can use v final equals a t, and we're going to put the average in there. I think that would be the way to go. We could use x equals vt, but we need the average v. We haven't figured out the average v. Actually, v average would be 0 plus this divided by 2. So that divided by 2, we could easily do that too, but we've already got a average, so let's just use that. We've got our v final, so we can just solve this one for t. So t is equal to v final divided by a average. I should be doing the bar over the top. That's what I should be doing. That's easier. So 7.17 times 10 to the minus 3, and that's meters per second. And then a average, what did we say that was? That is 5.92. 5.92 times 10 to the minus 7, and that's meters per second squared. And so obviously we're going to be left with seconds in the numerator is all we'll be left with. I think I have that number, 1.2 times 10 to the 4 seconds. So even though they're really traveling quite slow, if you turn 1.2 times 10 to the 4, so if we want to know how many minutes that is, or hours, 1.2 times 10 to the 4 seconds, And an hour, 1 hour is equal to 3,600 seconds. So if we do that, we're going to end up with 3.37 hours. So we didn't have to wait long for these two guys to stick together. All right, so if you're an astronaut, let's say you're an astronaut, and you're out in space and you're trying to get back to the space shuttle. There it is, out in space with all the blasters on the back, the jet engines, whatever, and it's got some wings. Okay, so here's your space shuttle, and you got your nice suit on. You're out there in space. If you have just the slightest velocity away from the space station or space shuttle or whatever the mass of this guy is not going to be enough to get you back, right? I mean, seriously, if your velocity is anything that's away from that shuttle and you're not tethered, you're in trouble. You got to have a tether. Okay, so I'm gonna put one of those anklet tethers on him, so he can't escape. Examples 13.1 for orbitals and 13.2 do exactly the same thing that we did above. So you can go through and look at those if you want to. They're pretty informative. I just thought I would tell you that. It's helpful to read the book. You already know that, I'm sure. So what we're going to do next is get rid of this right there. And we're going to start talking about gravity near the Earth's surface. So near the Earth's, E-A-R-T-H, Earth's surface. All right. So here's the Earth. And that's the radius of the Earth. And I need to... okay. So, what do we have? We have, say there's an object on the surface of the Earth. Okay, so there's a mass of the object, and then we've got the mass of the Earth, and we're going to be dividing out by the radius of the Earth squared. And I know I wrote it as a capital R, and I don't want it as a capital R. I want it as a little r. And then we're going to multiply it by gravity, gravitational constant, and this is the force of gravity. Okay, so watch this. M object times G. What does that mean? That means this is G. Okay? So G equals mass of the Earth divided by the radius of the Earth squared times the gravitational constant. And we typically use 9.8 meters per second squared. I just looked at one of the problems that I assigned for the homeworks a little bit ago, and at the North Pole, and this kind of makes sense, it needs to be a little bit larger at the North Pole. Why would it be larger at the North Pole? It's because you're not spinning around with the loss of the centripetal acceleration because of your spinning at the equator. You're at the North Pole. There's nothing throwing you away from the Earth. So at the North Pole, it's actually 9.83 meters per second squared. So I thought that was interesting, and you guys you'll see that. You'll see the problem that is. But at any rate, it's definitely different for different points on the surface of the Earth. So let's just look at Colorado landscape. So should we do it from west to east? So here's mountains. And then gradually you get down into the plains, and like say here's Denver. Okay, so we've got mountains up here, we've got Denver down there. The gravitational constant is going to be different here for Denver than it is up at the top of, I don't know, Long's Peak, right? I like Long's Peak. So there's the top of Long's Peak. The gravitational constant is going to be different there. Just for one fact that R of the Earth is different, right? In fact, Denver's a mile high, right? So down here, let's say that's sea level. G at sea level is going to be different. So all in all, G definitely changes around the world for many different reasons, okay? One is how high are you, and not in that regard. What I mean is what is your altitude or your distance away from the center of the Earth? There's that. There's what is your position on the Earth? Are you at the North Pole? Are you at the equator? If you notice, the Earth, actually when it's spinning around its axis, it bulges out. Okay, so it bulges out at the equator, and it's actually shorter. So it kind of does this kind of thing. And that's really what shape the Earth is. So there's a lot of reasons why you would have a greater gravitational constant here than here, I should say. That's your bulging out part right there. Okay. So that's here nor there. It's always roughly about 9.8. And let's just go with that. So, okay. What about a little bit further away from the Earth? So here's the Earth. Looks like Linus's head. And we've got, say, a satellite that circles the Earth. And let's put it at geosynchronous orbit. Do you guys know what geosynchronous is? Geosynchronous, that means here's the Earth spinning. We're going to put the sun over here. That's the correct spin. Okay, so sun, Earth is spinning. That means that this geosynchronous orbit, this guy stays exactly the same spot, over the same spot on Earth at all times. So it also goes in that direction, and it does it in exactly 1 day. So it rotates 2 pi per day. So omega equals 2 pi per day. Great. let's throw in some numbers. So we want to know, okay, here's the question. What's the question? What is G for a satellite at the height, HEI, GHT? Yeah. All right. Should I be a perfectionist for once? HEI, GHT at the height of a geosynchronous orbit. Geosynchronous orbit. Question mark. Okay, that's our question. What is the distance? I'm going to just tell you. The distance for a geosynchronous orbit above the surface of the Earth, so that's this distance here, is 3.58 times 10 to the 7 meters. We know what the radius of the Earth is. It's commonly known, and it's an average, of course. They don't include Mount Everest. Well, I mean, it's an average. I guess they do include it, but they also include the Marianas Trench. So, all right. Do they? No, that's underwater. They include the sea level. Okay, so here's the radius of the Earth. So our geo is equal to 4.21 times 10 to the 7 meters. All right. The mass of the Earth. What do we got? Mass of the Earth, that is 5.96 times 10 to the 24 kilograms. Should we eliminate these guys? All right. So we got that. Now all we have to do is figure out what geo is. So we've got the mass of the Earth. We're going to divide by r geo squared, and we're going to multiply by the gravitational constant. I'm not, in my notes, I don't have, I didn't put all the numbers in and do all that stuff. They're right here. So you can do that if you want to on your calculator. You might want to, just because sometimes I make mistakes a lot. And that's what we get as an acceleration at this point. So if we were to just look at the two different places, one at the surface of the planet, so GE for surface, Earth surface, that's 9.8, right? And if we're going all the way from 9.8 down to 0.22, that means that this radius had something to do with it, right? This total radius being as big as it is had a lot to do with causing this. Nothing else changed. This stayed the same. This stayed the same. The only thing that changed was that. So that's the difference, right? So the further away you are, the smaller the gravitational constant is going to be. Not the universal gravitational constant. the constant for the massive body. Okay, that's the massive body is this guy. All right. That's a geosynchronous orbit. And it's kind of far out there. Okay. But a standard orbit, a standard satellite orbit. Why did that not work right here? Satellite orbit. Okay. Is closer to D equals 400 kilometers. And this is for 40 million kilometers, right? Almost. It's 35.8 million kilometers. This satellite is a lot closer. Let's find out what that G, and we're just going to call it G orbit. We've got mass of the Earth. We're going to have the radius of the Earth plus 400 kilometers. And we're going to multiply all that by G. We're going to square that guy. This actually turns out to be relatively large, surprisingly large, right? So as you get closer to the Earth, it quickly increases the acceleration constant of gravity, of that force. So what is our next question? What do we got here? A writer wrote in with the question, what is R for geosynchronous orbit? What is R? Didn't we already figure out what is R? I don't know if I want to... I don't know if that's a question that I care about. But what I do want to know is... what is the omega for a geosynchronous orbit? How about that question? Let's solve that. So we're going to go back to a geosynchronous orbit. What? No, we don't want to know what that is. No, what? Omega for a geosynchronous orbit is just 1 day, 1 revolution per day. We don't care about that. Boom, boom, boom. What am I wanting here? Oh, I think I was calculating. Okay, I was just reaffirming something with a waste of time is what I was doing. You guys are good. I don't think you need to have everything verified like that. So instead, how much time we got? Okay, we're all right. Let's talk about gravitational fields. Oh, I keep doing that. Sorry, I hope that didn't hurt your brain. Gravitational fields. This is going to help you guys, hopefully, next next semester when you start going into E&M, because we're definitely going to be talking about E&M. And when I teach it, I go back to these gravitational fields and then help you assign the electromagnetic fields instead. So we're just going to look at a massive object, and we're going to have the fact that this massive object has a field that pulls objects into it, okay, equally on all sides. And that means that there is also what we call an equipotential. All these field lines are pointing toward the massive object. Our object has mass. At this point, G, everywhere along that, is that green? I hope it's green. If it's red, just forgive me. So that, whatever that is, whatever that color is for this equipotential, G is constant, equals a constant at all points along that equipotential, okay? But definitely G changes as we move in and out, okay, through the different equipotentials, right? You can think of it as a topographical map, and each of these equipotentials is just like an altitude line on a topographical map, and they get closer and closer, right, to this guy. So there. Okay. I hope you guys don't have too many questions about that. Those are our equipotentials. The Newtonian gravitational field. So, there we go. So Newtonian gravitational field. All right. So, what is that field? The field works like this. If I were to take an object, can I do another color? I hope you guys can see yellow. I can see yellow. So I'm going to put a yellow object right here. I can't see that. Okay, let's change that. I don't know what color this is, but I'm going to put that object right there. I'm just placing it, okay? It's a placed object. It has nothing to do with anything, but I'm putting that object there. That object is going to be drawn toward the mass, the main mass in the middle, okay? That means that the field that is pulling that object in has nothing to do with the mass. So the force that normally has m, big M, over r squared times g, this mass is it's sort of like a test mass. So what are we doing? We're placing that test mass into a field. What is the field? The field is gr, m for the mass, r squared for wherever we put our object, times g. okay? And then the direction is in the r hat direction, okay? This is, let's just get rid of this, okay? This guy right there is our Newtonian gravitational field, okay? That's it. And all we did was we put a test mass in our gravitational field, and once we do, we have m times gr, okay? And then we get a force. But until then, we don't have anything, we just have a field, okay? And the field looks like pointing toward the planet in blue, and it has equipotential lines in whatever that color is going around on the outside. Okay, I'm gonna try and get that color back because I like it. And if I didn't choose the right one, then you have to, again, I'm just trying to be helpful for you guys so you can see this stuff. Okay, it's a field, and all massive bodies have to obey this field, okay? So this field is the law. It's the law. All right, so here we go. Let me tell you a little bit of history. So it was 1915, and a paper was published. A paper came out paper on non-linear field equations. And I bet you guys know who did this paper. It was Einstein. Good job. So, came out with a paper. Now, the only reason I'm doing this is because I want to talk a little bit about set timer for 20 minutes. You guys are in for a treat. So Einstein came out with this, and he came out, and don't freak out, okay? This is not something you're going to need to know how to do, all right? Nobody is going to expect you to do this or know this. Okay. So Newton came up with his gravitational field. Okay, this is it, right? This is Newton. He did a great job in the 1600s for everything that he had technologically. He did a great job. Einstein did a wonderful, miraculous thing when he came out with this same stuff. And it turns out that this field encompasses that field. So if you were to break it down and get a case-by-case scenario, and you wanted to look at satellites or, I don't know, somebody on the top of Mount Everest, and you wanted to know what their force of gravity was for them, you could break this equation down, Einstein's equation. You can break that down, and you would get Newton's, okay? It would give you Newton's equation, all right? And it just happens to be more encompassing because it handles relativity and all the other stuff, the curvature of space and blah, blah, blah. So this G, this is the thing I wanted to show you guys. That G, not this one, This is a different G. In fact, we shouldn't even be using that G. I'm going to erase it. I don't like that G. That G is going to be turned into R mu nu, okay? But this G over here, guess what that G is? The universal gravitational constant. It's inescapable. It's there. It's definitely a thing, okay? So that gravitational constant is the same as Einstein's equation, and it shows up everywhere. Anytime you're going to be doing satellite stuff or putting a man on the moon again or whatever we're going to do, all that stuff is I'm trying to hit the right button. Okay, so Einstein's equation is great, okay? And I'm just throwing it out there because at the end of the chapter, they do talk a little bit about it, but I thought it would be nice for you guys to see it. I'll just tell you real quick, this is a tensor. This is a constant. This guy is a tensor. And that's a tensor. So anyway, nobody talks about those things in these classes, and I just thought I'd share that with you. I'm going to do another a little bit more in history. Okay, so we have in 1916 a fellow named Carl. So Einstein produced this paper, okay? He didn't solve the equation. He figured out that it works, and in case-by-case situations, it works, and it gives you Newton's laws, all right? But Carl Schwarzschild, I don't know how to pronounce it. Okay. He solved it. And here's the thing. I mean, the only reason I'm really telling you guys this is because it's incredible. So he solved that field equation. This is called a field equation, right? Because it gives you a field, just like Newton's universal gravitational field. This is a field equation. He solved the field equation. I'm going to shorten out equation with what is now called the Schwarzschild metric. Schwarzschild metric. Okay, and so here's the thing. That's not so incredible. Why is that turn? I don't think my pen is running out of juice. Okay, that's better. In 1914, Mr. Schwarzschild, KS we'll call him, joins the German army. And he had, so we could call it Germany or Deutschland, whatever. He joined the German army. All right. They were starting. I don't want to get into the whole politics of it because I really don't know a whole bunch about it anyway. But anyway, they were starting World War I back then, and he was all about it. He wanted to support the fatherland, and good for him. So he fought. Why am I capping everything? I'm just so excited about this guy. So he's on the Eastern Front. So the Eastern Front, the Western Front, and because he was good at math, he was an artillery. So he did artillery calculations. And then so they would shell everyone else with the guns, and he would design the trajectories for the shelling, okay, for the cannons. So he knew the parabolic equations and all that stuff that would do that. Fine. He was in trench warfare, all right? Trench warfare. And this is the situation that he did his work. He solved the whole thing in 1916. It took him some time, but while he was fighting, basically, he was in the trenches. It's amazing for me to even think of anybody who could do this, but I don't know why I wanted to put a parenthesis there. Okay, so he's in the trenches doing this. I just can't, I can't fathom it. He posts this, not to Instagram, but he posts it, puts it in the mail, and they publish everything. And 2 months later, he dies. And he picked up something out in the trenches that killed him. He just died of a disease. So, but it's certainly a disease that he picked up in World War I. So, I don't know if you guys have heard about it, but there's this thing called the Schwarzschild radius. And that comes from the study of black holes, because his metric allowed people to look at and imagine that there could be black holes. So it's his work that got us to that point. So they named that Schwarzschild radius after him. And there's some interesting things about a Schwarzschild radius. All objects have one. You have one, I have one. The Earth has one. But typically, the body of the object, the Schwarzschild radius, is inside the body, right? It's smaller than the external boundaries of the body. Makes sense, right? But if you have a supermassive object, the Schwarzschild radius the gravitational pressure of the body is so great that the body is inside the Schwarzschild radius. And this is what they call the event horizon. So, the event horizon, all right? And once you pass the event horizon, you're done. You're gone. You're not coming back. even if you get this close, you're probably in trouble. So spaghettification happening. All right. So that's enough about that. I think I'm going to stop here. How far do we have to go? I think I'm going to stop here. I don't think I'm going to stop here. I think I'm going to record another one. So, but we're going to stop at this point, and I'll have to record another one.